Pluto is far away from the Sun, of course, so the Sun is multiple times fainter than it is here on the planet. So, its freezing temperatures decrease to around minus 230 degrees Celsius during the evening time. In an intensity wave, you could get as high as 170 degrees Celsius. It has an extremely questionable environment too. Welcome, inquisitive minds, to an investigation beyond the recognizable domains of our solar system. Consider the possibility that I told you that Pluto, the far-off and mysterious Bantam planet, is at last taking its inestimable action, possibly crashing into none other than Neptune, the ice giant. Pluto's defiant nature has been apparent from the beginning, a rebel on the edges of our divine area. Its circle, daringly encountering another planet, challenges the ordinary standards of planetary conduct. I mean, that is no sort of lead for a planet, right? From the baffling complexities of Pluto's circle to the raised concerns voiced by astrophysical illuminators like Tyson and Kaku, a waiting inquiry hangs in the infinite equilibrium. Will these divine monsters participate in a crash course? Could the convergence of their paths spell unanticipated ramifications for our beloved planet Earth? Today, we set out on a grandiose journey filled with uncertainty. While the answers to these divine questions might escape us right now, the potential for an impact of such grandiose extent serves as a clear reminder that the universe is a stage for events both stunning and perhaps a bit terrifying. Join us as we dig into the secrets that circle how we might interpret Pluto and Neptune, examining the possibilities of a heavenly conflict that could reshape the infinite equilibrium of our planetary group. The stage is set, and the unfolding show entices us to witness the confounding dance of the planets among other potential space catastrophes. The universe harbors a variety of puzzlers, and among them is the perplexing riddle known as the three-body problem. Yet, scientists anticipate other likely upheavals within the divine theater. Although a planet crashing into another in space is highly unlikely, it isn't thoroughly out of the question. Gravitational interactions, as described by the three-body problem, are one of the forces that influence planetary orbits. An illustration of a space system where gravitational forces produce an occasional pattern known as orbital resonances is TRAPPIST-1, which has 7 planets the size of Earth. As time elapses, these patterns could weaken planet orbits, enhancing the probability of crashes. What is going on? Does it exclude any crashes? Despite the fact that systems, such as TRAPPIST-1, are very dense and planets influence one another's courses, especially when they are close, scientists consistently monitor these systems to figure out this. With this information, we can better grasp how the planets travel through space. Another obscure yet realized aspect is rogue planets, which float carelessly in space rather than in orbit around a star. Ejection of planets from star systems can happen as a result of gravitational tugs or other galactic peculiarities, such as another star's close approach or active instability in systems with more than one planet. Over time, these wandering planets can travel vast distances, potentially reaching areas far from where they originated. It is possible that they will run into other star systems on their solitary journey. The possibility of a planet crash increments if one of these planets goes to another nearby planet group. In any case, a rogue planet striking another planet head-on is very unlikely, considering how vast and mostly empty space is. The sparsity of planets in open space and the vastness of interstellar distances work together to deter frequent crashes. It is already highly unlikely that 2 rogue planets will impact. However, the frequency of rogue planets is far lower than that of stars and planets in stable orbits. The star systems involved can become chaotic in the event of a cosmic merger. It is highly unlikely that planets will impact head-on during these massive events due to the vast interstellar distances. The orbits of stars and planets within emerging systems are altered strongly by major areas of strength for the gravitational forces. A planet might become a rogue planet, liberated from any star, when this kind of disorder forces it out into the cold, dark depths of intergalactic space. On the other hand, planets could be ejected from their orbits, crash into each other, or even influence their host stars due to these gravitational disturbances. When gas and dust are compressed under extremely high pressure, gravitational collapse can actually cause new celestial bodies to form or perhaps start stars to emerge. In our solar system, the late heavy bombardment suggests that around 4 billion years ago, there was a period of increased impacts involving comets and asteroids. This surge in celestial activity is believed to have resulted from gravitational disturbances caused by the outer planets. During this turbulent phase, gas giants like Jupiter and Saturn were undergoing migration, disrupting the orbits of numerous smaller bodies in the Kuiper belt and asteroid belt. As a result, these smaller objects were thrown into eccentric paths, with many advancing into the inner solar system. This influx led to a significant rise in impacts on the terrestrial planets, including Earth. While these impacts didn't involve direct collisions between planets, they illustrate how gravitational interactions can bring about significant shifts in the trajectories of celestial bodies. This siege is thought to have played a pivotal role in shaping the surfaces and geological records of planets in our solar system. Additionally, it might have contributed to the distribution of water and organic materials to Earth, influencing the development of our planet over a long period. As stars go through changes in mass, flows, then portions of planets around them might wind up further and possibly cross. This is particularly noticeable in systems where stars are nearing the end of their life cycle. As a star advances in years and burns its nuclear fuel, it often goes through significant mass changes, especially during stages like the red giant phase or when it releases material in a planetary nebula. These variations in stellar mass can significantly affect the gravitational balance of the system, causing the orbits of neighboring planets to either move outward or become more compact. This is more likely to occur in multi-star systems where complex gravitational interactions can easily lead to unstable orbits. In such systems, the gravitational forces from multiple stars can interact unpredictably, exacerbating orbital disruption and increasing the chances of orbits converging. This can result in situations where planets could get captured by another star, crash into other celestial bodies, or even get catapulted into interstellar space. Pluto's unique orbit, initially recognized as a clear member of the planetary family, underwent a renaming, eventually being designated as a dwarf planet due to its distinctive orbit. The astronomy community is still enchanted by it and finds it interesting even with this alteration. There's reason to worry as to the closeness of Pluto's track to Neptune's. According to recent figures made by renowned scientists like Neil deGrasse Tyson and Michio Kaku, these scientists are sounding the alarm about a grave danger to Earth, the probability of an impact between the planets. Pluto is unlike any other planet in our local planetary group, and this is what makes its circle around the Sun so unique. Pluto has not completed a full revolution since its discovery in 1930, and its circle ranges an extended 248 years. The fact that it veers off significantly from the generally round circle of the huge planets makes its course extremely irregular. Further adding to its reputation, Pluto also has a more severe circle than other planets because its inclination to the ecliptic plane is 17 degrees. Adding unpredictability to Pluto's orbital pattern is the combination of its elliptical shape and inclination. The point where Pluto's circle runs into Neptune's is an interesting feature. During around 20 years in each circle, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their respective positions in the local planetary group. This leads to the question, why hasn't an impact between Pluto and Neptune happened? The explanation lies in the gravitational influences exerted by other planets. The assessment of Pluto's circle began shortly after its discovery, presenting a perplexing conundrum for astronomers. Unlike the majority of planets whose circles align relatively close to the ecliptic plane, Pluto's unique characteristics include a steep inclination and an elliptical shape. The mystery deepened with the realization that Pluto's circle crosses that of Neptune. The three-body problem, Pluto's circle remains stable amid the complexities, serving as a testament to the intrinsic complexities of celestial mechanics. Understanding the motion and gravitational interactions of three celestial bodies like Pluto, Neptune, and the Sun is known as the three-body problem in space. Predicting their trajectories from their initial positions and the effects of gravity on each other is similar. For Pluto, some of the terms that help to solve this astronomical mystery are azimuth libration, scope libration, and the VZK oscillation. According to astrophysicists, azimuth libration is vital because it keeps planets in their circles. When Pluto crosses Neptune's circle, it is something like 90 degrees distant, which is a critical distance that prevents impacts. According to this definition applied to Pluto and Neptune's scope libration, alluding to the upward movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is positioned primarily over their orbital plane, providing an extra layer of protection against crashes. A vital factor in understanding celestial motion is the VZK oscillation, named after three scientists, Van, Lee, and Kai. They explored the gravitational interactions between three space objects, such as Pluto, Neptune, and the Sun. The VZK oscillation figures out why Pluto's orbit around the Sun seems unusual but remains smooth over time despite the apparent irregularity in space. Hidden patterns and rules keep everything in check. These factors together stabilize Pluto's orbit, preventing collisions with Neptune or deviations from its course. The three-body issue helps us understand how the gravitational pulls of these space objects influence their path. Considering this enhances our understanding of Pluto, our local planetary group, and distant celestial bodies. Mathematical simulations in the late 1980s revealed that despite stable properties, Pluto's orbit is indeed chaotic, with minor initial deviations leading to significant differences over thousands of years. Despite this inherent chaos, Pluto's orbit demonstrates remarkable stability over extensive periods, effectively mitigating expected turbulence. Recent virtual simulations have expanded our understanding of the complex dynamics, including the influence of massive planets like Neptune, Jupiter, and Saturn on Pluto's path around the Sun. Neptune's distinct gravitational effect, completing 3 circles for every 2 of Pluto, significantly contributes to the overall stability of Pluto's orbital path. Jupiter's gravity is also significant, albeit less so than Saturn's. Taken together, these observations illustrate that Pluto is in secure and steady motion across space over billions of years. It is crucial to constantly observe and explore these events. Space exploration frequently reveals the unpredictable behavior of celestial bodies. Pluto's orbit is a classic example of this unpredictable behavior. It illustrates how minor changes in the dwarf planet's location or speed can profoundly affect its orbital path. Scientists' understanding of Pluto's movement in space is largely due to virtual simulations, which mimic the gravitational interactions between Pluto and other planetary bodies like Neptune. These simulations utilize complex mathematical models, allowing astronomers to see how small changes can significantly impact Pluto's path. The case of Pluto gives a vivid illustration of the concept of orbital chaos, demonstrating how the trajectory of a celestial body is highly dependent on its starting point. For centuries, scientists' understanding of Pluto's motion in space has been aided by virtual simulations. These models have revealed fascinating